Well, what do you understand from the word human-computer interaction? Well, it has three words: human and computer, and there is interaction. Well, obviously, the interaction is going to happen between the human and the computer. Okay? So it could probably have been better to name it human interaction computer, but then it doesn't make sense English-wise. Okay? Now, why do we have this course? Computers play a very important role in our life nowadays. Everywhere around you, you have computers. We use computers or digital machines to basically assist us in having a more efficient, more effective life, and helps us in making a lot of decisions. Okay? You have a cell phone, you use it in communication. That's a computer. Your university has a system that maintains your grades, and it makes it easier for you to know which grade you got in which course and why did you get this grade. Okay? Banks have computers, hospitals have computers, and so on. So they play a tremendous role nowadays, as you all know, in our lives. But these machines don't resemble us at all. They are simply electronic circuits. Okay? So on one side you have the machines that have their own design and architecture and specification and mode of working. And on the other side you have humans. We are very sophisticated creatures. We can do a lot of things that no one else can do in terms of the creatures that exist on planet Earth. Okay? We can think in a very sophisticated way. We can analyze things in a very sophisticated way. We have hands, we have arms, we have legs, we move around, we jump, we swim, we do things that are very unique to us. Now, we are supposed to be using computers to make our life easy. Okay? To do that, we have to use computers a lot. But computers are not like us. When you work with a computer, you're not working with another fellow human being, you're working with a machine. That machine does not have arms, does not have legs, does not move around. I'm talking here about, everything excluding robots. I spent some time towards the end of the course talking about human-robot interaction and why it's different. But what I'm talking about here is standard computers, like your desktop, your laptop, your tablet, your cell phone, and so on. Now, HCI as an area is part of computer science. It's actually the second latest addition to computer science. The one that came after it is social networks. And the focus of HCI is the facilitation of the using of digital machines. In other words, to enable us to use these digital machines in an easy way, in a smooth way, in a fluid way. Why there is an issue? Because digital machines are not like us. They don't understand English. They don't understand Arabic. They are basically just circuits. Okay, so you could think that HCI exists at the border between human society and all digital machines. The goal of HCI is to enable human society to use digital machines effectively, efficiently, in an enjoyable way, in a smooth way, in a fluid way, to accomplish whatever we would like to accomplish. Okay? Now, again, why wasn't it designed from the beginning so we don't need HCI? The thing is, most digital machines, most digital innovations are done by electronics engineers and computer engineers. And those have little knowledge about HCI. They are more focused on the design process, the physical design process, the PCB layout, the sensor design, and so on. They don't really take the human into consideration. So most engineering activities are task-centered around the design process. It's not about the human. Okay? Plus, our knowledge and our state of understanding of electronics does not allow us to just, jump directly from an idea to a robot that does the functionality we would like to do that looks exactly like a human being. Okay? So what we end up designing is something that's quite primitive. If you have used Zigbee in any one of your projects before, or if you have used any embedded system, you know how primitive they are. And after you design it and it's working, it's doing the job it's supposed to be doing, the question is, how would you interact with this machine? And this is where HCI is what HCI is trying to address. Okay? So one question we should ask ourselves here is, HCI focusing on human society or on digital machines? And the answer, probably to your surprise, we're focusing more on the humans. Why? Because to design something that is usable, that is enjoyable, that is efficient, that is effective for the human, you have to study the human. You don't have to study the digital machine. And this is what surprised people when they start studying HCI. They actually discover that most of the time in HCI, we're not talking about software, we're not talking about hardware, we're talking about humans. What do humans like? How do humans move? How do humans see? Okay? It's not about how you render color on the screen, it's about what is a good color for a human. Okay? So this is something that you always need to remember, that HCI is human focused. It's not software focused, it's not hardware focused. Now, for that, and because of that, HCI is a multidisciplinary area. If you look at the chart at the bottom, these are the areas from which we draw knowledge in HCI to be able to do work. So neurophysiology contributes to us in HCI because we use neurophysiology to learn about how the human think and how the muscles move, and how the brain sends instructions, for example, to the muscles to move a muscle, okay, and so on. And we use psychology to understand how the human sees things around him or her, how he thinks of processes that he's involved in. We use linguistics to understand how messages should be sent or displayed to the user. We use anthropology to study a group of users in a specific location, for example in a factory, to understand how to design a system that will help them in the manufacturing process. Okay? And obviously we need to know computer science and computer engineering because we need to know how to do interfaces and how to do hardware and what are the limits of software and hardware. Okay? So there are many areas contributing to HCI. Now, usually, multidisciplinary areas like HCI or biomedical engineering or mechatronics are fun to learn because they draw from many other majors, and you need to combine your findings from the different majors to come up with something that is new or innovative, but also it makes it relatively harder than areas that are self-contained, like for example differential equations or operating systems. Okay, it's just an area that is self-contained where most of the researchers who contribute to the advancement of the area are from within the same area. Okay, when you get an area that has so many fields contributing to it, it becomes a lot more enjoyable to work in, but also a little bit harder. And throughout the course you will notice that we're not really talking a lot about software or hardware. We're talking a lot about findings from psychology, findings from neurophysiology, okay, findings from linguistics. Okay, so the course covers things like theories about how do humans use words to think. Okay, and we will talk about Chomsky theory of using words. Okay, and then when we talk about psychology, we are going to talk about something called gestalts that is part of perceptual psychology, and we'll talk about different branches of psychology, perceptual psychology and cognitive psychology and so on. Now, but remember, we're not doing this outside the umbrella of computer science. HCI is still part of computer science. Okay? Historically, by the way, it was not called HCI. It was called and was not part of computer science. the kind of the father or the mother of HCI is another area called ergonomics. So this predates HCI, and most of the stuff that we talk about today was the first time it was used in a non or in a industrial context was in ergonomics. Ergonomics is the study of how you make a machine, a physical machine, that will not harm the labor working in front of it. So in ergonomics, which was part of mechanical engineering, they also drew on information from psychology, from a specific branch of psychology called motor psychology, and they also drew on techniques from anthropology to design physical machines, the machines you see in any factory if you've ever went to a factory. Okay? When digital machines appeared, they are machines as well, but they are digital. HCI was founded to solve kind of parallel problems, how to work with digital machines. So while ergonomics is about how to work with physical machines, HCI is about how to work with digital machines. But it is still under the umbrella of computer science, because we learn all of what we learn from the different areas to be able to design an interface. And an interface sits on the top of the software logic, so it's still computer science. So within HCI, there are four main areas. There is the area of input devices, which is how you input a piece of information or instruction to the digital world or to the digital machine you're working with. And there are output devices, how you display information from the digital machine to the user. And there is an associated area with input and output devices called interaction techniques, which is how you use an input device or an output device to do continuous interaction with the digital machine. And there is a fourth area, which is the design and evaluation of traditional interfaces. Okay? So I could actually split HCI into two very broad categories: HCI research and HCI in the industry. HCI research is about the design and evaluation of new input and output devices and interaction techniques. For example, the screen you see here above the phrase output devices, this is an actual screen. This is not a mock-up. This is what's called a 3D volumetric display. This is made by a company in the States called Actuality, and what this is actually a plate that rotates very fast, that has a piece of cloth on it, and there are projectors at the bottom. With every angle in the rotation cycle of 360 degrees, with every angle a different image is projected. So what you get is a suspended actual physical 3D model in space. What that means, if you go from the back of the screen, you're going to see one side of the mountain that is displayed there, and if you go from the front of the screen, you see a different side. Now, this is one of the goals of output device manufacturers and researchers, is to be able to display physical 3D, real 3D. Remember, our screens are flat. They're not 3D. We can create virtual 3D by creating, like computer games, by creating 3D characters that move on the 2D screen. And we get this illusion that it is 3D. But what we're looking at here is real 3D. Okay? Now, the problem is, if you look at this screen, we have no idea if anyone actually invents a commercially feasible, realistic, accurate rendering 3D screen. How do we interact with it? Because there is physical depths here. In 2D screens, we don't have physical depths. So here, the mouse that we use, for example, to move around in a 2D screen, in a 2D interface like the Windows interface or the Mac interface, will not help us here, because here you need to go inside. You need to move inside, not X and Y alone, but also Z. Okay? So with every new output device, with every new input device, we design new interaction techniques. And even for existing input devices and output devices like the standard mouse or the standard keyboard, there are new interaction techniques being designed, and we will talk a lot about interaction techniques. Now, I have deliberately put the image of Tom Cruise here doing this interaction technique with these gloves that have LEDs in them. This is a screenshot from the movie Minority Report. This is actually the movie that made, or one of the movies that made HCI very popular, or at least it introduced HCI to the general public, because people start thinking, oh, we can do this. Now, I've put it here deliberately because all the interactions that Tom Cruise does in the movie are all wrong. They look fancy. They made people say, whoa, this is really nice. But from an HCI point of view, they're all badly designed, and we will talk about them in time. Okay? So there is a difference between something, and this is the message here, there is a difference between an interaction technique that looks nice and that is designed correct. Okay? Usually stuff that looks nice are because of their what is called exhibitory effect, that they make people excited because of the type of action that you do. Like, for example, here, when he was putting his hands forward and rotating through images of people's memories or people's dreams, okay, which are basically events that will happen in the future. It looks very fancy, okay? You can see some of the pictures at the bottom in his shirt, but everything he does is just plain wrong. Okay, if I'm designing this system, or anyone who knows anything about HCI actually designing a system to navigate through pictures, you would never, come up with the design that was used in the movie. Okay. Now, just like the output devices I'm showing you here, there are a lot of innovations in the input devices world. Okay. So, for example, what you see on the right, above the word input or the phrase input devices, you have a glove that has sensors that you put in your hand and you use to move a cursor. So it is a replacement of a mouse. Why would you need that? Perhaps you don't have a flat surface to use a mouse on. So this is perhaps could be a device that be used by a pilot in an aeroplane where there is no surface, or because the airplane is moving up and down because of the air pumps. So you need an ability to control a mouse cursor without having a flat surface. So probably that's one option. Or you could use it perhaps underwater. Okay. So again, there is no notion of a flat surface. Now, interestingly, if you look at the image at the left, this is actually the first ever invented mouse. Okay, it was invented by a researcher called Engelbert. We'll talk about him later on. It was made out of wood, and you can see the button. It had only one button that appears on the far right of the corner of the image. Okay, so all those three areas, input devices, output devices, and interaction techniques, are HCI research areas. Now, this is one half, or no, actually it's not more, it's more than one half. It's probably 3/4 of HCI. Okay, that's what most HCIers would be interested in, how you come up with a new device, or how you interact with a new device, or how you enhance the interaction with an existing device, whether input or output. Now, there is a little area of HCI, a little mean that it does not occupy a lot of space in the HCI typical mental activity, because it's more of the standards that people use to develop interfaces. So input devices, output devices, and their interaction techniques are all research-oriented activities. Okay, people design a lot of input devices, people design a lot of output devices, and they do lots of research on them. Many of them will never reach to the market, will never be commercial because of different reasons, but some of them will. And when they reach to the mass market and people adopt them, like for example nowadays, the cell phone and Android platform or the iOS platform, what actually happens is that a standard is put by the user interface designers to teach programmers who are building interfaces how to build it properly according to the rules of this specific environment. So if you're building an application for Android, there are rules how you can actually build an application for Android interface. Okay, there's something called the drawer, for example, and what you put in the drawer are certain functionalities. Okay, same thing for iOS. Okay, now when you're building traditional interfaces, you need guidelines to make sure that even though you did not violate the rules of user interface building in the specific platform, there are still an opportunity for you to produce a bad interface by not understanding the foundational information that exists, in HCI. So for that reason, there is a whole kind of sub area that some HCIers work on, that is actually they work on for the purpose of helping developers to build better commercial interfaces. It's called UX. Okay, so you must have heard the term before, like UX design. Okay, now UX design or UX rules or UX as a sub area of HCI draws a lot on the foundational information that every HCIer learn. This is the information we get from psychology, all the branches of psychology, perceptual, motor, and cognitive. This is the information we get from linguistics. This is the information we get, or the learning we get from neurophysiology, and so on. Okay. Now, I also cover in this course UX design. Okay, but I only focus on it as a small part of the course because the rest of the course will serve you in UX design. It will serve you indirectly because once you learn the rest of the course, for you UX design will be common sense when I start to talk about it. Okay, because you've already learned the foundations. Okay, so one thing to take from here as well is that UX design is not HCI. Okay, UX design is an area within HCI and is made for designing practical, specifically commercial interfaces. Okay, it's the point where you want to give instructions to a programmer to build an application that will be released to the general public. Then you apply or you look for UX design activity. Okay, but as an HCI researcher, I'm not just interested in UX design. Okay, because again, UX design is built on foundational information that we use in research. So I'm going to teach you both, but the focus is not going to be just UX. Okay, but they all kind of feed into each other. So the course content is mostly 80% of it is preparing you to design and implement a new type of an interface. This will help you in many aspects. It will help you to actually kind of break yourself from thinking using the traditional interface. Okay, traditional interfaces are what you see on Windows, what you see on Mac OS, what you see on Android, what you see on iPhone. Okay, non-traditional interfaces are the new interfaces, the ones that are not yet available to the general public. They are coming from an HCI, typically an HCI researcher, and they are doing things in quite a different way. Okay? For example, a number of HCI researchers have worked for a while on designing 3D user interfaces, totally 3D. So when you log into your desktop, you don't see anymore the flat screen and the files and folders that you're used to. What you see is a 3D world. Okay? There was actually even a company at one point called, I believe, 3DNA, yeah, and but they went bankrupt nowadays. What they did is they actually, when you log in, you see yourself inside a 3D home, and you could buy your own model of a home, and you organize your files in cabinets in a drawer, in drawers in a cabinet in the office. So if you would like to open, say, your assignment to work on, you navigate just like you navigate in a 3D game inside a house. You climb up the stairs, you open the door, the room door, the office door, and then You go to the cabinet, you open the drawer, and you scroll through the files, and then you take out a file, and when you start reading it, the screen becomes a little bit 2D, okay, like or the scene itself becomes a little bit 2D, I mean, okay. So this is an example of a completely different interface than what you're used to. Okay, I will show you later on an interface that was made by a researcher, and actually Google bought the company because they were quite concerned that actually it might impact their business. So I spend 80% of the time on that, and the nice thing about it, there's lots of new ideas. The feedback I get from students actually most of the time is that they really like the innovation part in the course. Now, because we're talking a lot about new interfaces, okay? We don't talk about traditional interfaces. I'm not going to teach you how to design a menu or how to program a menu or how to create a dialogue, okay? So we spend 80% of the time doing that. And then 20% of the time of the course we're spending on designing and evaluating, and mostly evaluating standard user interfaces, okay? Which is the UX stuff, okay? Now, this might sound like a lot, and also a little bit challenging, because if I tell you design a new interface that you have not seen before, it's not Windows, it's not iOS, it's not Android, it's something that you have not seen before. How can you go about that? Well, there are things you have to learn. For example, we will talk about basic input tasks. If you design an interface, you better support some, if not all, of the basic input tasks, depending on what is the interface is made for. For example, if you're building a new interface for a labor factory, or labor, I mean someone who's working in a factory, okay, you don't need all the input tasks. For example, he won't type because his hands are busy with the production line. So we will talk about things to consider when you're designing a new interface, okay? But you also need to understand and appreciate and learn a lot about anthropology, psychology, linguistics, industrial design, and neurophysiology, okay? And as well communication theory. We'll talk about that later. So most of the really, really good designers in the history of HCI had very strong background, not just in either computer science or computer engineering, but in one of the other areas as well, okay? So design is not, this is not art, by the way. Like I'm not teaching art. HCI is not like art. In art, you can just improvise, and you come up with your own new thing, your own production, your own imagination. Okay? No, this is science. So it's built on foundational information that has been proven to be correct. Okay? Based on experiments, based on scientific findings, and so on. And we build on that, and we use that. Okay? So what are you going to study? As I mentioned, HCI is human focused. Okay, that's why the H appears first in the word HCI. We're going to study a lot of things about the human being. Okay, we're going to study his brain, how the brain works. We're going to study the eye. We're going to study the vision. We're going to study the different muscles, the classification of muscles, how muscles move. Okay, and we're going to study also the skin and how can you actually use the skin to take output or put input into the user body. So we're going to study a lot of that. Now, but when we are studying it, we are actually, I'm not teaching you a medical course. Okay, so while we're going to use a lot of information from physiology and neurophysiology, but I'm delivering the information with the focus of how actually can we use that. So I will not be interested in, the really intricate details, the chemical reactions that happen, except for, a few area, a small area or a small part of the course. But in most of the cases, I'm teaching you, okay, this is how this organ is, this is how it works, and these are the different pieces, the relevant pieces to us, and then this is how we use it in HCI. Okay, so I'm more like HCI focused, this is not a medical course. So I will not go into unnecessary details related to the physiological aspects of the human being. We are also going to study a number of theories from psychology. So let me first explain the difference between psychology and psychiatry. Psychiatry is a branch of medical studies. It's the study and treatment of mentally ill individuals. Now, psychology is the study of normal individuals who are not suffering from any mental illness, with the goal of trying to understand how do humans make decisions or see things or move around in the environment. So it sounds a lot like medical studies, except it's done on people who are not having any kind of medical mental challenges. Now, psychology attracts lots of researchers from different areas. You could find actually some medical doctors very interested in cognitive psychology because it relates to what they are doing. Now, generally, there are three major branches of psychology. Cognitive psychology, which is the study of the human brain and how it behaves and how it works. And perceptual psychology, which is the study of perception, of us being aware of the environment around us, whether through our eyes or through our ears or through our skin, and so on. And motor psychology, which is how do humans move. Now, this is very important for us in HCI because if we are going to design a good interface, whether it's software or hardware, we have to understand how the human behaves, how the human is constructed. So the construction part we cover when we talk about the human anatomy, but the behavioral part we cover when we talk about the different parts of psychology that we're going to cover. So we're going to cover concepts and theories from cognitive psychology and from perceptual psychology and also from motor psychology. Now, in order to be prepared for HCI research, which is one of the goals of this course, we're going to discuss in detail how you design an experiment and how you analyze the data that you collect from an experiment. Now, this is actually a very, very important piece of information that you will learn, or an area that you will learn and will get extensive exposure to during this course. This topic of experiment design and statistical analysis. And I always lament the fact that you're learning this in your final year. In my opinion, you should get this information when you enter the university in the first semester, because it kind of changed the way you think about science, and you will develop an in-depth knowledge of the power of the scientific method and of doing experiments, and also the limitations associated with that. So you are neither ignorant of the fact that we need scientific research, we need scientific experiment, but you're also not under the illusion that you can find all answers using experiments and scientific and using the scientific method. So it's kind of put a very I would say I put a very concentrated amount of effort on making sure that you understand what is experiment design is all about, what's an experiment is all about, and how you analyze the data and how you critique the data. If you are actually a business student and you are taking this course, the information here is also very valuable to you, because whatever I discuss in experiment design is done in market research and is done in market analysis as well, and it's done also in collecting feedback about a specific product in the market. So the information is actually quite applicable to the business domain as well. In fact, it is applicable to all domains. If you're studying chemistry, you need experiment design. If you're studying physics, you need experiment design. If you're studying engineering, you need experiment design. Okay. If you're studying business, if you're studying computer science, you need experiment design, not just HCI. Okay. So we'll talk more about this in detail, and this is one of the topics that students always find extremely interesting in this course. So watch for that lecture. So let's start the course. So the first human organ we're going to look at and study is the human eye. Now, why the eye? Because we use our eyes to see the interface. And what draws our eyes in an interface is the use of colors. This is one of the very first things that attracts our eye. So the use of color could either improve how an interface is, or it could actually affect the user experience negatively. So we're going to understand what colors should be used in an interface by understanding how the eye sees a color, or how do we see a color. Let me first do this test. I want you to look at this image for a few seconds and tell me what are you seeing or experiencing. Now, within a few seconds, you should feel the image is moving. Now, by the way, this is not an animated GIF. This is just a simple static image. The reason why you are actually feeling this strange visual effect that it is actually moving, and in fact, if you keep looking at it, you might get a little bit dizzy, is because of how this image is composed. So what we're going to do is we're going to study what is currently happening to your eye as you keep looking at this image. So the human vision system depends on two components. The first component is the wavelengths of light that is going through your eyes, and the photoreceptors inside your eyes. So let's first start by talking about the wavelengths. Now I will return back to your physics background. You have studied electromagnetism throughout your school years, pre the university. You know there is something called the electromagnetic spectrum, which is the spectrum of all radiations that exist around us. What we see using our eyes are electromagnetic radiation with the wavelengths of 400 nanometers to 780 nanometers. This is what we describe as visible light. This is what we could see with our eyes as humans. By the way, other creatures, you might already know this, see different things because the spectrum of their visible light, for example, in the case of cats, is different from us. So they would see other things we cannot see. The whole spectrum is quite big. It ranges from 10 to the power minus 6 for cosmic rays all the way till very high wavelengths, which are TV and radio wavelengths. Now, if you're wondering about cats, you're still interested to learn about this, the cat's spectrum and the dog spectrum are shifted to the right and the left of us. So both each one of them, each species would see different things from the other. Okay. Now, so light is all about wavelengths. Remember that. Okay. Why there is a range 400 nanometers to 780 nanometers? Because every color has a different wavelength. This is what makes a color different. It's just the wavelength is different, nothing else. Now, what we describe as visible light has what we call a color spectrum, or falls within our color spectrum. At the far end, I'm referring to the image at the bottom left of the slide. At the far end, we have violet, which is close to 400 nanometers, all the way till red, which is close to 700 nanometers. So anything that you describe as color is just a different wavelength. That's what is one wavelength from another. Of course, here I need to mention something you should have learned before. I'm sure you did, which is that it sounds a bit funny, but really there is no colors. The way the world works around us is that every material has a property that distinguish it from other materials, which is how much it absorbs of light energy. And what it doesn't absorb is reflected back. The amount that's reflected back is basically the remainder of the energy that was not absorbed. And that is the wavelength. That has a specific wavelength, and that will be the color. So really, there are no colors. There's no violet, there's no green, there's no red, there's no blue, there's no yellow, okay? There's nothing. There's just electromagnetic radiation, and based on its wavelengths, we see a different color, or we think we are seeing a different color, but it's just a different wavelengths, okay? We've given it the names that we use. We've given the wavelengths of 575 the name yellow, okay? But it's really could have been given another name, like for example blue, okay? But we agree what is yellow, okay? Now, so let's go back to physics. There is a relation between wavelengths and frequencies. The bigger the wavelengths, the smaller the frequency, okay? Think of this as energy. So if the energy vibration is very fast, then the frequency is high. And if the frequency is high, then the wavelength is short. This is what shows up in the right image in the right graph at the bottom. It says high frequency and short wavelengths. So if you think of a specific unit of time, if the oscillation is high within, say, 1 second, compared to a low oscillation within the same 1 second, what that results to is that the speed of travel of the energy is going to be slower, and consequently the wavelength is longer and or bigger, and the frequency is smaller. So they are the opposite of each other, okay? So wavelengths and frequency are the opposite of one another. Big wavelengths means small frequency. Small wavelengths means a big frequency or high frequency. Now, returning back to the basic idea that this is an energy moving in space, okay? I've written down at the bottom of the slide a very important observation which affects how we see things, which is that the shorter wavelengths, the higher the frequency, we just mentioned that, the less penetrance, okay? The less penetrance means the following. If the oscillation is high, the frequency is high, the electromagnetic radiation is going to consume its energy fast. So it will penetrate less, it will travel less. However, if it is slow, it will maintain some of its energy as it keeps traveling, so it will, if the frequency is low and the wavelength is big, then it will penetrate more. So let's refer back to our color chart at the left, our color spectrum. When we say, for example, that violet is 400 nanometers wavelengths, let's compare this to red, which is 700 nanometers wavelengths. Now, if again the wavelength is small, the frequency is high. That's what's even written there, higher frequency. If the frequency is high, the energy is consumed or lost faster. So violet will penetrate less. Red, on the other hand, has lower frequency, and consequently, as you see, 700 nanometers in terms of wavelengths, it has higher wavelengths, so it will penetrate more. So starting from the same point, red will travel further compared to violet, and this is an important observation. Now let's go to our eye and understand how our eye is built. What you see on the right side is an image of a cross-cut sectional area of a human face. As you see, the eye is like a ball. You should already know that. And there are muscles attached to the eye, which is itself is a muscle. These muscles, as you see, they are labeled in red, are attached to our skeleton. If you notice, there are two types of muscles. Muscles at the top and muscles at the side. The reason behind having muscles at the top and muscles at the side, to stretch the eye horizontally and vertically, the eyeball itself, to stretch it horizontally and vertically. Now let's go to the left image. Now in the left image, what you see is a cross-cut sectional area of the eye itself. At the front of the eye you have the pupil, which people refer to in terms of the eye color, and then behind it there is the lens, and then behind it there is a big chamber that has what's called the vitreous humor, which is a liquid that exists inside our eye. There's a very important area at the back of the eye called the fovea, which is in a region usually called the macula. The fovea is the center, or you could say the region in the eye that the image has to fall on to get sharp vision. So it plays a very important role in our perception of things through our eye. Now just below the fovea you can see what's called the optic nerve, which takes the information to the brain. Where is the information that we are seeing is coming from? Throughout our eye, from the inside, there is a layer called the retina. It's written just above the fovea. This spans all inside what we call the eye, the ball from the inside. Retina consists of sensors that gets activated when electromagnetic radiation falls on it. These sensors will send electrical signals that gets collected at the optic nerve, and then that travels to the brain. Now let's go back to the fovea. If you're wearing eyeglasses because your vision has degraded over time, if you're a computer scientist, that's probably a must. Now you put on eyeglasses to correct your vision. What that really means is to make sure that the electromagnetic radiation that's going through your eye, whatever you're seeing, the colors, that whatever you're looking at, will intersect exactly at the fovea. If you take away your glasses, you start seeing a blurred image. That blurred image is because the electromagnetic radiation, the light that's going through your eye, is not intersecting at the fovea, it's intersecting somewhere else, a little bit in front of the fovea. So the intersection has to be exactly on the fovea, so you see sharp vision. Okay? Now let's try to put the pieces together. We've talked about the color, we've talked about the wavelengths and the frequency. We have reached to a very important conclusion that the shorter wavelengths travels less. Right? So the shorter wavelengths, as ultraviolet, we said it's the 400 nanometers. Since the wavelength is small, the frequency is going to be high, the energy is going to be consumed fast, so it will not travel a lot. Okay? Now, on the other hand, the longer wavelengths, like red, will travel very far away compared to ultraviolet. What that means, the following. Let's consider the case of you looking at 5 objects. Each one of them is of a different color. I have put the colors in the figure at the bottom. One object is blue, another one is green, the third one is yellow, the fourth one is orange, and the fifth one is red. We said this is nothing but energy. Each one has a different wavelength, consequently a different frequency. We will go from red, which has the highest penetrance, to less penetrance, which is the blue. Now, where is the penetrance happening here? The object is in front of you. The light rays are traveling and going through your eye. They penetrate your lens through the vitreous humor, the liquid that's inside the eye, and they intersect somewhere inside your eye. For you to see sharp vision, the intersection, which is drawn inside the eye here, has to be exactly on the fovea. But if that happens for one of them, it for sure will not happen for the other ones, because the fovea is supposed to be in place, in a specific place. And this is really the role of the muscles that I described earlier. The muscles stretches your eye horizontally and vertically all the time. You're not feeling it, to make sure that for every color that goes through your eye, the color intersects. The light rays from that color, that specific color, intersect specifically on the fovea. Okay? So your eyes are actually moving all the time. You just don't feel it. Okay? This is again to consolidate this concept. Every electromagnetic radiation will travel for some distance when it enters a liquid or a space or a media, as it's often described in physics. If you're using a convex lens so that the light rays converge and intersect somewhere, and that's the lens in our eye, it's a convex lens, the intersection is going to happen in different regions. Now, obviously, I'm talking here about differences that are all in nanometers. So it's incredibly small, but it makes a difference in how you see things. If you don't get the intersection exactly on the fovea and 1 nanometer in front of it or 1 nanometer behind it, you're going to see blurred vision. And this is again the role of your muscles, the muscles in the eye, which appear here at the bottom of the slide, the image at the bottom right. The muscles are stretching your eye horizontally and vertically to make sure that for every color that goes through your eye, the intersection is happening at the fovea. Now, you might say, how does it know, or the brain or the muscles, how does it know how much to stretch or relax? Well, this is actually what happens. Whenever you see something, you don't see it sharp vision focused at the first instance. What you will see first is a blurred image, but you don't feel that. And then the blurred image is sent to the brain. The brain realizes this is a blurred image, so it sends instructions to those muscles to stretch your eye horizontally and vertically, and it keeps doing that until you see sharp vision. And that all happens in less than a millisecond, so you really are not aware of it. But it's happening all the time throughout your life. Whenever you are actually awake and you're seeing things, that's always happening. A blurred vision detected by the brain sends instructions to the muscle stretches and your eye horizontally and vertically, and there is a continuous correction of that muscle movement until you get sharp vision. Now, if you imagine the amount of work your eye muscles are doing, by the time some people are old, when they reach to old age, their vision starts to deteriorate. And part of the deterioration that happens is that the muscles get tired. So if someone reaches the age of 70 or 80, regardless of the glasses they are putting on, their vision is just never as sharp as it used to be because the muscles themselves gets tired. There's also something else. One of the worst things you can do is that within a very short duration of time, you force the brain to stretches the eye horizontally and vertically so quickly that you feel it. Okay, if you actually start feeling that your eye is moving, or the eye is jumping around, or actually the image in front of you is jumping around, it's moving, then you're really stressing your eye. This is actually what happens when you keep looking at this image. You will suddenly feel the image is moving. The image is not moving, it's your eye being stretched horizontally and vertically, extremely fast, trying to get any kind of focus vision for any color. And if you actually look closely at the image, you will notice that it is made of curves where every curve is the whole spectrum. You can see that by just looking at the spectrum at the bottom. It goes from violet to blue to cyan to green to yellow to red, orange to red. That's actually what each one of those curves is made of. And consequently, your eye is picking any color and trying to focus, but then another color goes into your eye, so it tries to focus again and again, and consequently you start feeling tired because of just looking at this image. Now let's dive further into the eye. In the retina, there are photoreceptors, or basically light sensors. They are of two types: the rods, and these are called rods because they look like a rod. They are displayed at the image at the bottom, and cones. The rods are actually responsible for your perception in dim light, okay, or night vision. So if you should have noticed actually that when the light goes off and there is no light source at all, you can still see, but you don't see colors. You see shades, or shades of gray, okay? Who would be sending that information? Who's currently working in your eye? It's the rods, okay? The rods are sensitive to changes in shades of gray. They are not sensitive to color. They don't fire electrical pulses when color falls on them. They fire electrical pulses in the dark when they detect changes in the shades of gray or the level of darkness around you. This is how you see in the dark, okay? Now, the cones, on the other hand, is responsible for your color vision. In order to see color, there must be light. It cannot be dark. And whenever there is light, the cones starts working. The cones will emit electrical signals that corresponds to color. Okay? So you are seeing colors because of your cones, and they are called cones because they look like a cone, which is visible in the chart at the bottom right. And notice that the rods and the cones are all connected to a nerve system that all connects back to the optic nerve, which goes directly to your brain. So these rods and cones are organs that emit what you can think of as an electrical current, very, very small, based on the fall of electromagnetic radiation on it. Okay, it gets activated by electromagnetic radiation. Now, let's learn about the rods and the cones. The first thing is, rods and cones are not equally distributed in the retina. We said the retina is the thin layer that lines the inside of your eye ball, your eyeball. Now, the center of the retina has a lot of cones. Okay? The edges of the retina has a lot of rods. This is what shows up at the chart or the graph at the bottom. What you see at the left side is a cross-sectional cut of the eye with the fovea at angle 0. And then as we travel up, the angle increases all the way till 80. And then as we travel up the other direction, also the angle increases all the way till 80. What you see on the graph is angle 0 at the x-axis in the center, and then there is 10 to 70 or 80 on one side and 0 to 80 on the other side. The red line represents the number of cones. So as you see at angle 0 at the fovea, you have a huge number of cones. It's close to 150,000. And as you deviate away, or as you move away from angle 0 to angle 10 to 20 to 30, the fovea is actually, the cones are actually way less. They drop significantly starting from angle 10. Now, the blue line is for the rods. The rods are concentrated on the periphery. So at angle 80 or 70, 60, 40, 50, you see there are lots and lots of rods, and they peak at angle 20. And then there is a huge drop in their numbers to the point that there is none at the fovea at angle 0. And this exists on both sides of the chart. Now, there is obviously a gap in the middle of the retina, which is the opening through which the optic nerve departs the eye going to the brain. That is, in all humans, is called a blind spot because there are no photoreceptors, because it's just an opening, it's an outlet through which the optic nerve travel. And this is obviously important for us because this is how the signal reaches the brain. Now, let's think about this finding that we are describing here, that the cones are concentrated at the fovea and they decrease significantly on the periphery, and the rods are concentrated in the periphery and they are non-existent at the fovea. What that means is at the sides, what's called the peripheral vision, okay, what lies close to your, at the right side of your vision and at the left side of your vision, you have more capability to detect changes in shades of gray, while at the center you have better capability or best capability to see color, which is a great design, I would say, because if something exists on your right, isn't it enough that you know the general details and you don't care about color? While if something exists in front of you, wouldn't you be interested to see the colors, to inspect it carefully? Okay? For some, biologists, they would tell you, oh, this is a survival actually property, because if you're standing in the forest and the lion is coming towards you, you don't need to see its colors. You just need to figure out, oh, there's actually a lion coming towards me. You will see that due to changes in the shades of gray. Okay? You don't actually need to bother about whether it has golden hair or it's a lioness. Okay, so this design actually will imply certain things as when we talk about this later, when we try to talk about it from an SI point of view. For example, I'm just going to give you some insight about what we're going to talk about. There are certain displays called peripheral displays. There is even certain displays, some interfaces are called also ambient interfaces, which are interfaces trying to communicate information to you through the periphery. So while you're working, you get feedback about certain processes you're interested in. And those are usually in the periphery of your vision. Okay, they're not at the focus of your vision, and since it's the case, it's better to actually change their shades of gray, not to use actually colors. So you don't go from, say, black to red
to signify danger, you go from white to shades of gray to signify danger. If this is a peripheral display or an ambient display, we'll talk about this later on. But I'm telling you that this has implications on how we design things or design interfaces. The story doesn't stop here. Now here's the issue. We have three types of cones. We have blue cones, green cones, and red cones. Now if you have taken a computer graphics course, you have done any kind of programming or any kind of image manipulation, you know that there's something called the RGB system. And this actually RGB system is coming from our eyes, okay? It wasn't invented aside from our eyes, it's how we see things. So there are three cone types: blue cones, green cones, and red cones. What do I mean by a green cone or a blue cone or a red cone? I mean that this is a cone that gets activated most when a green color, if this is the green cone, it gets activated most when a green color falls on it. So let's put some hypothetical model. Let's say that the amount of electricity that gets emitted from the cone varies from 0 microvolt to 10 microvolts. For a green cone, when a green color falls on it, it will emit 10 microvolts. Okay? For a red cone, when a red color falls on it, it will emit 10 microvolts, the maximum. For a blue cone, when a blue color falls on it, it will emit 10 microvolts. Okay? So this is what's called, that the sensitivity of the cone. So each cone is sensitive to a specific, basically, electromagnetic radiation or wavelengths, okay, or frequency. So they're not all the same, okay? Now, if you're looking at an object that has complex colors, I mean a color made up of red, green, and blue, like 50% blue, 50%, 25% green, and 25% red, okay? All the cones will fire. If I say it's 50% blue, then the blue cones are going to fire because there is blue color. And if I say 25% green of it, then there are green color. So the green cones will fire, okay? And if there's also red, if I say the remaining 25% of the object color is red, then also the red cones are going to fire, okay? If you're looking at an object that is pure green, nothing else but green, only the green cones will fire, okay? The blue and red will not. And it goes like this. Now, the brain identifies colors. When we look at two colors and we say this color is different from this color, it's because the amount of firing that happens from the cones are different. So in the brain, somehow there are a process that says, okay, if I get 10 microvolts from the green cone and nothing else, this is going to be what we call in our culture green, okay? If I get 50% green and 50% red, so I get like 5 microvolts from the green cones and 5 microvolts from the red cones, I'm going to get that some other name, okay? So our brain is basically associating the readings it gets, the amount of electricity, the amount of current it gets from the cones with the cultural names that we have associated with. Now, here is the issue, and this is really why we're talking about this at this point, The cones are not equally distributed in our retina. What we have as humans is 64% of the cones are red, 32% of the cones are green. So most of our cones are actually red. And then 32% or 1/3 is green, and then only 4% is blue. Okay? And not just that, but the fovea has a very small number of blue cones. Okay? So we are actually not good in looking at the blue color or focusing on the blue color. You might be asking me, okay, why do you have the background blue? I will tell you shortly why do I have it as blue. Okay? So that you don't see it. But I will talk about that later. Now, what this means is that our eyes or our vision system has a color sensitivity that is not equal to all colors. In other words, it's not sensitive to all colors with the same amount. The sensitivity comes from the amount of firing that happens from the cones. So the more firing, the more we are sensitive to that color, because when we orient our face to an object that has that color, the firing happens right away. So we become alerted to the existence of that object because of its color. Okay? So the highest sensitivity, obviously, is if we activate all of the reds and all of the greens. So we are activating in this way 96% of our cones. Okay? So a color that is 50% pure red, 50% pure green, or two objects, one of them placed beside each other, one of them is pure red, completely pure red, and the other one is completely pure green, and you're looking at both at the same time, then you are going to get the high sensitivity. Okay? Now, if an object is 50% red and 50% green, it's actually a yellow object. Okay? Because yellow is made up of red and green. So what that means, if you would like to attract someone's eye in a user interface, then use the yellow color. This is why I have my lecture slides, the title is in yellow. So trying to prevent you to lose concentration, when you use color that attracts the eye, the brain starts working by processing what it's seeing. So you immediately look at the lecture slides and you notice the title. So maybe you're more attracted to the content. Okay? The chart you see at the bottom right is telling us about the sensitivity of all the colors in the spectrum. What you see at the bottom of the chart is the whole spectrum from 400 nanometers to 700 nanometers. If you look at yellow, which is about 550 nanometers, you get an intersection of the green and the red lines. And this is why we have the high sensitivity for yellow, because all of the green and all of the red are working. For any color that you could think of, there will be, unless it's pure. Pure means there's only one component in it. If the color is a complex or a composed color or composed of several colors, the red, green, and blue will fire depending on how much blue, how much green, and how much red is in the color. Okay? And that defines the sensitivity of that specific color. So if you look at the color that is pure blue, then you're talking about the sensitivity curve that is drawn in blue here. Now notice that I will only activate, if it's pure blue, then it's 450 nanometers. That's the highest sensitivity to blue, so the blue cones will fire, but the blue cones is just 4%. Okay? So what reaches the brain in terms of what we are seeing is 4% of the total that could be reached or could be sent on the optic nerve. So it is less noticeable. Or if you like to think of it the other way around, it is harder to perceive, because the amount of information sent to the brain is minimal, because you only have 4% of the cones are blue. Okay? If you would like me to draw an analogy here so you get a sense of this, okay? Imagine if you get a cup of water and you add a teaspoon of salt, and then you dissolve it and you drink it. You will notice there is actually salt in the water. But if you grab 1 grain of salt and you throw it in the water, or let's say 4% of a teaspoon, okay, and you dissolve it in the water and then you drink it, you will not notice it. Okay, it would just, the water will look like a bit funny, but it's not really salty. You don't know what's going on. Okay, because 4% of a teaspoon is like almost nothing. It's just like a little, few number of droplets of salt. Okay. Now we need to talk about colors a little bit, since we know all of this. Okay, there is a whole branch of perceptual psychology called color theory. They discuss researchers investigate how we actually see colors and how we should talk about colors. Okay? So, a very famous theory that has influenced all of us. It's called the trichromatic theory. The theory is that since our cones are red, green, and blue, let's talk about colors in terms of red, green, and blue. This is what computer graphics, early researchers did. They figured out, okay, since we have colors now inside a computer, how can we talk about it? Well, they studied the trichromatic theory and they developed the RGB system accordingly. You know that an image consists of pixels, and a pixel consists of 3 values, red, green, and blue. Okay, it's a direct one-to-one mapping of the theory that was put in perceptual psychology to what we actually do in computer graphics. Okay. Now, in the trichromatic theory, it goes like this. We have 3 primary colors, red, green, and blue, which maps to our visual system or our cones. However, if you actually are designing an interface for a non-human user, a dog or a cat or a bird like the one I've put here, okay? In fact, I have recently learned that there's a very small minority of women, of females on Earth, who have tetrachromatic vision system, and this is only in females, okay? What that means is they don't have 3 cones, they have 4 cones. And I found that quite amazing. I didn't actually know about this until a few weeks back. Now, they are obviously perceiving colors differently than us, okay? But let's think of the bird example. Okay, if you design an interface for a bird, you have to understand that most birds have tetrachromatic vision. So they have 4 cones. So you have to design the whole system so that the colors encode the 4 components. Okay? Now, I believe I'm going to revise these lecture slides, having known now about females, that some of them actually have tetrachromatic vision, so that I actually add more comments about that. Okay? But since I just knew about this recently, I didn't change the slide. So I like to talk about birds because, there has been a recent trend in HCI research to design interfaces for animals, okay? Especially dogs, because there are lots of dogs kept as pets in Europe and North America, and there are now devices popping up for dogs. So we even have now a section in major HCI conferences related to interfaces for animals. Yeah. Okay, sounds a bit ridiculous, but this is what it is. Yeah. So in the trichromatic theory, we have 3 primary colors, red, green, and blue. And we're going to get all other colors by mixing them, by mixing the 3. Okay? So if you mix green and red, you get yellow. If you mix blue and green, you get cyan, and it goes like this. Okay? So these would be called secondary colors because they are output of mixing primary colors. And then if you keep mixing, you get what's called tertiary colors. Okay, and you could think that the perimeter of the circle here that has these colors, you could generate any possible color by mixing these colors together. Okay, so this is all, I believe, is not really new to you if you have any experience with images or graphics. But here's the thing, the RGB model lacks one important dimension, which is the intensity of the color. When you talk about RGB, if you've opened any image in any photo editor like Adobe Photoshop and so on, you basically see 3 values, red, green, and blue. But there is nothing in red, green, and blue that tells you how much this is bright, how much this is dark. And there's a problem there. Because of this information lacking, we can't map RGB values to how the eye behaves. Because the cones will send out a different electrical signal depending on how much light or darkness exists in a color. So you could have light red and you could have dark red. The response of the cone is related to how much light is light and how much dark is dark. Okay? Now RGB does not have this. Let's just say RGB, red, green, and blue, and that's it. Okay? So there is another model that you would find HCI researchers telling you use it, don't use RGB, which is the HSV model, the hue saturation value model. Okay? Now in the hue saturation value model, what we described before as color, okay, is the hue. You could think of this as the pigment. Okay? So there is the hue red, and there is the hue cyan, and there is the hue green, and there is the hue blue. But this is just what we refer to as the color. There are other two dimensions that we need to be aware of. Around the perimeter of the hue circle that exists here, you have what we call the pure version of the color. So the red that is displayed here is pure red, which means there is nothing else but red. Okay? So going back to our simplistic model, the red cones are going to fire 10 volts current if this pure red is the color it is looking at. But what if the color is not pure red? It's not going to fire that much microvolts. Okay? How can you change red and still have it red? You can add more white, so it becomes a little bit desaturated, we say. And this is the saturation axis that is described here. So the more white you add to the color, the more it becomes lighter. Okay? Now, and actually the less response from the cones when it sees it. If you keep adding white, you will reach the white color because you will erase the original color, what you started with the hue. Okay, so the white is actually in the center where we think of this as no color. Okay, now if you start adding black, you're adding what we call value. If you start adding darkness, you are adding what we call value in this model. Okay, so you keep adding value until you reach to black. So there's two things here you can play with in terms of any hue. You can add white to decrease its saturation, and you can add black to increase its value. Okay? So again, if you add to a hue white, a little bit of white, you are making it less saturated. Less saturated from the original color, the red for example. Okay? You're making it a little bit whiter, we would say. So we can move along the saturation axis by going to the further out of the circle, which means I'm making it purely saturated or more saturated, or I could move towards the inside of the center of the circle where I make it less saturated, which means more white. Or I could move down by adding more black. Okay? So this is the same axis we are looking at, the same model with some color variations of red, so you get an essence of what I'm describing. I have at the further out of the circle a pure red, saturated red. If I just keep adding white, I will go all the way to the center where it's white. If I move with an axis adding a little bit of black, then I am decreasing the saturation of red and I'm increasing the value of red. Okay, obviously I go at the bottom of this chart where I can go to pure black. Okay, and this is again another example with just the red color displayed along the saturation axis and along the value axis. All of these are red except obviously the way at the bottom the pure black and the way at the top the pure white. Everything else here, the rest is red. Variation of red, which means the red cones is going to respond, is going to send out some electrical signal when it sees any of this. But it's going to be a different electrical signal. Okay? The strongest one is going to be for the pure saturated red, which is at the top row in the far right. And then the signal starts to diminish as you go away. You add saturation or you add value. Now, let's try to put pieces together. We said we see an object because it reflects light into our eyes. We know from physics days way back that if the object absorbs all the light waves, it's black. If it reflects all the light waves, it's white. If it absorbs some and reflects other, it is some color. Okay? Now, let me ask you this. At the bottom of this slide, you have the object reflectance map of some object. It says this is an example spectrum with a bluish hue. So this is actually a blue object, but it's not pure blue. It has a lot of blue, it has some green, it has some yellow, it has some orange, and it has some red. And it also has some violet at the beginning that is a little bit more than anything else beside the blue. So this is a bluish violetish object with some other light component, color components. Okay? This is an object reflectance map or chart as what it says in the y-axis, which means this is what it reflected. So in other words, it absorbed a lot of yellow, but not all the yellow. It reflected some yellow. It absorbed most of the red, but not all the red. It reflected some red. Okay? When it comes to the blue, apparently it didn't absorb a lot of blue. It reflected most of the blue, because that's why we're going to see it as blue, as a blue object. Okay? So let me ask you this. If that is the colors, obviously this is a composite color. This is an object that is, has a composite color. It's not at all a pure color. Let me ask you this. Which sensors, which cones or which sensors in the eye will fire? Obviously the blue will fire, but the yellow also will fire. The yellow will fire? Yes, but how will the yellow fire? Because we said yellow is made up of green and red. So green and red will fire. In fact, for sure green and red will fire, because I have here green and I have red, but I will also get some firing from the yellow color, which means again the green and blue, green and red will fire. Okay, and obviously blue will fire. Okay, so this is an example of some color that will cause all the cones to fire some electrical signal as output. Not necessarily a very strong signal in the case of the green and red, but for sure in the case of blue it will be a strong signal coming out from those cones. Now let me ask you this, having said all that. Look at these two charts. At the chart on the right, it says high saturation. This is an object that is blue, but it's saturated blue or close to be saturated blue, because you have very, very little from the other color components. And on the left, you have an object that, we were looking at before, more or less. It's blue and a lot of other stuff, okay? You have a significant green, you have a little bit red, but you have also some yellow. So we said again, yellow is red and green, so red and green are gonna fire. Green for sure is gonna fire. Blue for sure is gonna fire, okay? Now the question is, which one is easy on the eye? And the second question is, which one is shocking to the eye or attracts the eye? So I'm going to leave you for a few seconds just to think of this. So I hope you reached the correct answer. It is easier for the eye to see low saturated objects, because low saturated colors means there is no one color component that is dominant. There's a number of them, and consequently you have more chance of firing more cones. Like here at the left image, the blue cones are going to fire, but we said these are 4%. But also the green and red are going to fire. On the right side, only the blue will fire. Okay? So how you tie this with how the vision system works. Remember, we said this is how you see things. You actually look at something, the image that you see in the brain, or the brain receives, is going to be blurred. The brain instructs the muscles to stretch the eye up and horizontally to get sharp vision. Once sharp vision is reached, the brain is happy. With a low saturated color, the chance of reaching to that is faster, because any amount of movement that will happen might result in getting some sharp vision, because you have several color components. Okay? Now let's say the last object you were looking at was green. And then when you're looking at this new object at the left, the fovea was moved to see green sharply. Now you are going to see the object sharply at the left because you already, without doing any movement, because it has enough green. It happens to have enough green. Okay? Now on the right, you need to refocus the fovea so you get sharp vision of a blue object. So always with low saturation, there is a chance that you move the eye less. There is a chance that the fovea is not far away from the correct location to see sharp vision. With highly saturated objects, or generally with any object that is highly saturated color, red, green, or blue, or whatever. Notice here I'm referring to saturation, I'm not referring to just color. So you have to think of the HSV model. With high saturation, you're going to focus, you do a little bit more work to focus on the fovea so that you get the sharp vision. Okay? So low saturation is easier on the eye. Okay? High saturation is the reverse. Now, let's actually answer the second question. Which one will alert the eye? The high saturation will alert the eye, because the brain has just done a little bit more work to actually see that object. So it's going to be, you would say, more aware of it, of its presence, because it's more saturated. Okay? I hope you got this. So let's put some takeaways. We have been discussing lots of theory, lots of foundational information. Let's put some course takeaways that you need to use in your HCI design activity from now on. Okay? The first takeaway is going to be use saturated colors only when you need something to stand out. We've already mentioned that looking at and perceiving an object with saturated colors requires a little bit more effort from the brain to readjust the eye so that the fovea resides at the perfect location to get, or the exact location to get sharp vision. So anything that is saturated will always stand out. Okay? Now, it is not a good idea to make everything standing out, unless contrary to the common belief that you want your interface to stand out, so let's make everything saturated. No, actually, you are actually reflecting something. You are saying that you want the user to be alert to you, and yeah, sure, the user should be alert to you, but he shouldn't be too much alerted, I would say. So you have to use it cautiously. Okay? If you use it all the time, it's just irritating to the user. Saturated colors in general reflect that you're trying to attract the user attention. But if you keep attracting his attention too much, it's going to be annoying. Okay? Now, so when would you use it in an interface? You would use saturated color in an interface if you want to tell the user, pay attention. Okay? For example, displaying an error message, or displaying an important message in general. Okay? Now, so the general rule is we would like to use desaturated colors. The question is, which desaturated colors to use? We have two variations now. We either can use desaturated bright colors or desaturated dark colors. So the bright and dark here is referring to the value axis. Okay? Now, the most friendly of the two is the desaturated bright colors. The desaturated bright colors are basically easier to see because there is a number of colors used in making that non-saturated or desaturated color, as we said before. So the cones are going to fire, a good number of cones are going to fire enough information to the brain to know what the color is without actually doing a lot of eye adjustment. But with the bright color, you are actually taking the user or working with the user at his pace. You're not asking him to be a little bit more alert than what he should be. Okay? Now you might be wondering, why is that? Well, let's look at desaturated dark colors. Okay? Now desaturated dark colors means you've added value. You've added value. Now it is desaturated, but you've added black. Now remember, in the eye we have the rods, and the rods respond to shades of gray. When you start adding shades of gray or darkness into a color, the rods come into play. And the rods activating along with the cones alert the user more. So usually desaturated dark colors will communicate to the user feeling of seriousness, alertness, formality. Okay? This is just because of the physiology of the eye. We didn't really talk yet about the psychology of the color. Okay? So generally, desaturated dark colors is when you want to say to the user, we are serious, we're formal, we are doing business, we are of integrity, take us seriously. Who would use this? Banks, hospitals, governments, okay? News agencies or news websites. Desaturated bright colors is when you want to let the user be relaxed. You don't want to take him into a serious mode. Okay? So blogging websites, feminine websites, e-commerce websites, of course. With some cautious, I would say, but generally e-commerce websites, you don't want the user to be too alert, because if he's too alert, he probably is not going to buy. Okay? So desaturated bright colors is, we're friendly, we're happy, we're friends, buy from us. Desaturated dark colors, we're serious, take us seriously, let's be formal, let's do business in a formal way. Okay? Now, both of them has to be desaturated because you don't want to attract his attention too much, as I already mentioned. So I hope this is clear now in terms of how you think of colors. Now, I'm really talking here in terms of the HSV model, because without it, all this does not make sense. So when I talk about saturated, again, I mean the saturation axis. When I talk about desaturated, I mean I'm going from pure saturation towards the white, and now I'm introducing the value, whether it's dark or light. Now, the third takeaway is I would like to avoid pure blue for text lines and small shapes. Why? We have 4% cones. Okay? We are very weak in terms of seeing the blue color. Okay? So you never display your text in blue. You never display your messages in blue. Okay? The opposite takeaway is blue is great for backgrounds, because when you listen to or watch a lecture slide, what you're looking at is the text and you're ignoring the background, and I'm helping you ignoring the background by making it blue, because you only have 4% cones that is blue, so you can immediately, your brain can easily filter them out. Imagine I have made this background yellow, so your eye will always be attracted to the background, not the text. Okay? So the best actually color combination for lecture slides, or for any actually slides, is to make the background blue. Okay? Or some shade of blue. Okay? Not white, by the way. Okay? Because white attracts the eye more, but blue is not. Okay? Also, another takeaway is you avoid blue on dark colors. Okay? Generally avoid blue, except for background. But if you are going to use blue for some weird reason, then avoid dark colors with blue. Why? As we age, the vitreous humor inside our eye becomes disturbed. Okay? Disturbed means there are some residues of the oxidation process that hangs in the liquid. And consequently, it is difficult for the eye to penetrate, for the light to penetrate through this liquid to reach the fovea. Okay? So darker colors are harder to penetrate, And since the penetration is already being challenged by the residues of objects inside the aqueous humor, and if you use blue, then like it's complete disaster because darker colors will not penetrate and you only have 4% blue. So basically you're telling the user like, don't look at this because you'll not be able to read it, okay? So if you're designing an interface, remember, for someone who's senior, you have to worry about this stuff. Obviously, if you're designing an interface for, young people, maybe it's not that a big deal. But if you're designing, for example, a website to buy medications, so you would expect most of your users will be senior, okay? So you have to think carefully about what are the changes that happens to the eye. And one of the things is with old age, darker colors become harder to see, okay? Now the sixth takeaway is that, and this is really one of the major takeaways here, is that you avoid spectrally distant saturated colors. What does that mean? When you're picking a color choice or a color template for a website, avoid picking saturated colors that lie on different further away regions from each other on the chart. For example, you would pick something that's 402 nanometers, some degree of violet, and then as a saturated color, and then pick another saturated color in the middle, like green 550, and then you pick another saturated color that's 680, for example, which is close to being red. Now, what you're just doing in this interface, you're making the eye doing a lot of work to jump between those three saturated colors on the chart, okay? Or basically because they are further away on the chart. So if you decide to use two or three saturated colors, then pick ones that are closer to each other. That's assuming you need to use saturated colors in the first place, or you need to use more than one saturated color in the first place, okay? And this is actually what the chart you were looking at that was jumping in front of you was doing. It was all built off saturated colors. That's why your eye was jumping all over the place with the moving image, okay? Now, the seventh takeaway is that use yellow to attract attention. Okay, yellow is actually the color of choice if you would like to display an icon to the user that tells him something went wrong. Okay, it is not red, by the way, because you will often see in the streets, for example, the signs on the streets that tell you don't park here. Although in Egypt this is like a bit ridiculous, everyone parks everywhere, but the sign would be displayed in red, and while actually the best choice is yellow. Okay, and this has been showing up recently in Egyptian streets, where you start seeing a lot of shops, a lot of new businesses who really now think of color, having their logo or the background of their logo displayed in yellow, because now they understand if you're walking in a street and this is far away, the best thing is actually to look at it in yellow colors. Now, another takeaway is to avoid color in the periphery. We already discussed this before. In the periphery, we have rods, we don't have cones. So if you're displaying on a screen that is going to be on the periphery of the user, okay? An example here, nowadays in malls, they would put screens in front of shops or inside the display of shops to attract customers by displaying the different items they have inside their shop. So basically you pass by a shop like Adidas or Timberland or whatever, and you have this screen inside the display that keeps displaying the objects. Now if you're walking by, this display is going to be either on your right or on your left. So when you first see it, you're going to see it using your peripheral vision, unless you decide to change your orientation and face the screen and see what is being displayed. Now you're going to use your peripheral vision, and your peripheral vision is full of rods. So it is a bad idea to actually, if you would like to attract the attention of the customer, to display the images in color. It is actually better if you display it in shades of gray. So it changes from light gray to dark gray. The change will be more alerting to the customer, because the rods will be activated more than the cones because of their lack in the periphery. Okay, so the rods are more in the periphery than in the cones. Okay, there is an issue we have to keep in mind when we are deciding on colors for a website or an interface. which is that a percentage of the population in every country suffers from some level of what is called color blindness. So there are two main types. In the first type, the cones are not performing as fine resolution detectors of colors as they should. So changes or small changes between colors are not noticeable. So if you pick colors for such a group of users, you want to have high contrast between the colors that are used, because if you pick two colors that are close to each other, for example, dark blue and a little bit lighter blue, or dark red and a little bit lighter red, they will not see the difference. They will just see it as red or as blue. So you would need to worry about picking colors or color variations that are close to each other, because they will not see the variation. This is one class of color blindness. Now, the other major class is what's called the red-green deficient color blindness, or red-green color deficiency. Now, in these patients, or in these users' case, they either have no green cones or have no red cones. So what they're actually going to see in terms of color is something else that is quite unexpected. Okay? So, and some of them will not have even green and red. So they will lack both. Okay? So I have put images for you to understand what are these users would be seeing in the next slides. So someone who is blue and yellow colorblind, so he has some deficiency in terms of blue, red, and green, they would see the colors differently. Okay? Look at the different squares that are included here, and for every one on the left, the one on the right is different. Okay? Basically, they're not seeing any yellow. Okay? The yellow becomes something else. And they're not seeing any proper blue. They are seeing a variation of blue that is different from the one on the left. So the image on the left is what a typical, normal user would see, and the image on the right is what someone with color blindness would see. Okay? This is just one type of color blindness. There are many types, many combinations of red, green, or blue, and which degree of red, green, and blue. Okay? Usually the user will not discover it until late in age. They would not know that they have an issue with colors. Okay? Usually it would be like when they get married, or they go out with friends to buy clothes, and they discover that actually they're not seeing what everyone is seeing. Okay? So they would believe that what they're seeing is the norm, and then suddenly someone would tell them that actually this is not the color you're seeing. It's supposed to be something else. Now, or there is this. Okay, what you see on the left is what a normal user would see, and then what you see on the right is basically someone who has no cones working. Okay, his cones are there, but they're not firing properly. Basically, they're firing the same level of electrical current all the time, so the brain is seeing the same picture all the time. Okay, or the same color all the time. There's really no color. It's just shades of gray. Okay, so the cones act like the rods, but now in daylight. Okay. Now, how do we handle this class of users? Okay. There are two approaches. There is something you must not do, and there is an additional effort you can do. What you must not do at all is to communicate information using colors. To rely on the color to deliver information. Like, for example, here in this form, the user filled some of the text fields and didn't fill another ones. So the programmer who programmed this form is using color to tell the user that, oh, you have to enter your last name, you have to enter your country, you have to enter your shipping methods. So the red here signifies like an error. The problem is, if you're in the States and 9% of the population have some level of color blindness, they might not see the red, so they will be wondering what's going on. Like, I don't know what's wrong, because you didn't display any message. You're just, the user is just saying, we found, or the programmer is just saying, we found an error while verifying your shipping address. We've marked the problem in red for you, but he can't see the red, okay? So don't rely on color to actually communicate information about the interface. Okay? Now, this is a must. This will be a takeaway. But what you can do as extra is to provide an interface for someone who's colorblind. Okay? And very few websites actually will do that, because this means you will have to redesign the whole website. Color scheme with the buttons and everything, okay, to do that. But this is the more kind of, I would say, civilized approach to handling color blindness, which is to have an option that the user can switch the colors being used in the whole website or in the whole software to match his type of color blindness. And it's not going to be one type, so you will end up designing several color themes for every type of color blindness, okay? So the takeaway is, this is for sure what you should not use. Do not use colors to communicate information to the user, okay? Now, we're going to move to another topic. We're now wrapping the color stuff, but we really need to talk about the psychology of color. So there is a branch in psychology called psychology of color, okay? The study of the cultural and conceptual and emotional meaning of colors. This has little to do with the anatomy of the eye. It has to do with history of a particular society. In every society on Earth, colors was used to reflect certain ideas, certain principles, certain imaginative pictures. For example, in Islam, the color green reflects the color of paradise. So you will find many Islamic countries or countries with predominantly Muslim population having a flag that is green in color. Okay, even Egypt, the old flag was green, and this has been going on for a little bit more than 1,000 years. That the flag is green because it's the color of paradise. Okay, this is not about the wavelengths of green. It's about what green represents culturally. Okay. Even the current Egyptian flag, which is has red and has black. Red is for blood, and black is for mourning, and white is for being peaceful. So all countries have history. This is what gives meaning to life. And people, in order to respect their history, they would keep the meaning associated with a specific color. So it's very important when you go to a place and you're designing an interface is to understand the culture. For example, in Egypt, it is uncommon to see a male wearing a pink or a pant or a pink shirt, because pink is associated with feminism. So if you go to an African country, in the sub-Saharan Africa or south of that, the color pink is a cheerful color. It's not necessarily that much feminine. Okay. The combination of colors also. If you look at the traditional clothes worn by African presidents, for example, you will notice that they combine lots of colors, which is not customary in Egypt. So when you go to a place, you have to understand the culture, okay? The very interesting case is the case of blue. Blue, across many cultures, have been associated with projecting safety and security. If you've traveled anywhere in Europe, or in the States, or in Canada, you would notice that the police is wearing dark blue. Dark blue reflects the message of justice and respect us, and that we're trustworthy. Okay? Historically, this comes from the tradition in Europe of knights wearing blue coats. In fact, they were even sometimes called blue coats. Okay? So this cultural dimension is important. it's as important as the psychology or the physiology of color. The anatomy of the eye and the cones and the reds and so on. It's not enough. You have to understand the culture to be able to communicate with the people through the user interface. Okay? And there are actually lots of studies made by color psychologists about this topic. They would go to a place and investigate the use of colors and investigate the cultural meaning by interviewing people and publishing papers about that. Okay? So I've put here a link for you to check what does each color mean in different parts of the world. Okay? Very recently, there has been a number of studies on Middle Eastern countries like Egypt and Syria and Jordan and Lebanon and so on. And there are similarities between obviously all the colors, but there are also differences. So you need to learn about the meaning of colors from a cultural point of view. Okay? Let me show you some examples. A classical example are news agencies. News agencies have always been accused of being biased. And if you want to tell people, trust us, then go to the culture and pick the right color. So if you access Al Jazeera, for example, they always had this blue theme all over the place. Okay? This is not just Al Jazeera. Al Jazeera is a recent news channel. Older news channels as well did so. If you look at Fox News, again, it's a variation of blue. Okay? Now, you go on to inviting people to play a video or to take an action. If you go to eBay, for example, you will notice that all the buttons are in blue. Okay? Especially, let's say, is add to shopping cart or buy this. Okay? You will rarely see a deviation of that because blue means trust us. Blue means play this. Blue means play it and you will not regret. Watch this and you will not regret. Trust us. Okay? Now, this is another example of what I'm mentioning. You see that all the buttons in eBay are in blue. It's like trust us, sign in and we will protect your information. Okay? Or search and we will get you the right results. Okay? So it's not by accident that it's blue. It has a cultural dimension. We already talked about blue being not a good color to see, but because of its cultural dimension, if it's used, sparingly in an interface, not everywhere, but in critical places, it will reflect trust. Okay? And the classical example of the use of blue is obviously Blue Nile, which was a company that was the first company online that was trying to sell jewelry online, which sounds like a crazy idea. Imagine like you would like to buy a piece of jewelry to your fiancé, or some of your female relatives would like to piece a piece of jewelry, so they order it online and it arrives in the mail. Okay, jewelry is very expensive. It might get lost and you will lose your money in the mail. It might get stolen, and plus there is something about buying jewelry. It's a very personal experience. Usually all families will have their own jewelry shop that they trust and they have been buying from since generations. So it's quite uncommon to buy jewelry online. Okay. Plus you can't really try it out and you can't really see how beautiful it is in a picture. So Blue Nile had a major problem trying to sell jewelry online. And the response was, let's make it blue. Everywhere it's blue. It's even called Blue Nile. Okay, like please trust us. We will get you the jewelry you want in. Okay. Now sometimes organizations deviate from one cultural theme to another cultural theme or color. For example, CNN historically was always blue. They always adopted the blue color. Okay. But CNN, in a very crowded news companies market, the business is very, very crowded place, especially with the existence of the internet. CNN wanted to differentiate itself, and the differentiation was that we are everywhere. CNN, I mean that they cover news everywhere. They have news reporters everywhere. They're extremely dynamic. They will deliver the news faster than anyone else. And consequently, they changed their theme to reflect this vitality, because red in the Western culture is for vitality and vigilance and dynamic behavior and dynamic actions, okay, and speed. So that's what they're trying to communicate. Like, now, by the way, in these cultural meanings of color, some might say that I don't feel that. I just see a red color, and that's perfectly okay. Not everyone will do, but when psychology researchers would conduct surveys and questionnaires about the use of color, usually most people, not necessarily like 99%, but more than 50% would say, oh, okay, this is more dynamic. Okay, so there's an element of relativity in the meaning of color and the use of color. Okay, it's not globally unanimous, but still more than 50% would agree that, okay, this reflects so and so. Now, some companies would move from one color theme to another for whatever reason. For example, BBC, again in a very crowded market, the market of news agencies, switched from blue, historically they used to be blue, to black to reflect seriousness and formality of the British news agency. That we are really serious. We would never get you any crappy news. So they switched to black as because black is really formal in the Western culture and in many cultures. We are serious people. Okay. So again, here the choice is a bit subjective, but there's a reason behind it. It's not just because black looks nice. If you go to Harrods, for example, for many years, Harrods' color theme was maroon, and the reason why, if you've been into Britain, and you've lived there for a while, you know that maroon is the color of the British royal family. This is the color they like. Okay. And consequently, since Harrods wants to project, oh, we are the place where nobility go, the royals of Europe are buying from us, so they made it as, and we are also a British institution, so they made the color theme as maroon. So the takeaway is that make sure your color selection process takes the cultural dimension into consideration. Okay, it's very important. It makes a big difference in the perception of the interface on the user side. Now, to select colors, you don't have to, if you're not into graphics design, if you're not into colors, you don't have to reinvent the wheel. I have put for you here links to websites that will do that, so you don't actually have to try to innovate graphics-wise. You can use similar services to generate the proper set of matching colors. You just have to keep in mind what we discussed in this lecture about how you choose the colors. So you can keep generating combinations of colors that match, and you consider what we've discussed today in the lecture, and then you have a color theme for a website or a user interface.